Okay, hi physics students. I'm going to show you how to solve these problems. First of all, grab your assignment. You'll need your equation sheet for sure. We're looking here in the resistors in series and parallel section. You're going to need, of course, a calculator. I would recommend that you work in pencil and not in pen. And most important of all for these problems, because we make tons of mistakes, grab your eraser. All right, let's get started. So the first problem says calculate the current and the voltage drop through each of these resistors. Okay, just want to point out right now, we can see that the positive side of the battery is over here. So the way we conventionally draw the current is it's going to come out and going to flow that way in a counterclockwise motion. All right, so what we want to do, of course, is we need to break this down, or this is one way we're going to do it, but this is the traditional way. We're going to break this down into one equivalent resistance. All right, so we redraw everything. This is not a demonstration or a tutorial on equivalent resistances, but you should know that resistors in series, add up and produce a total resistance. I'm going to call that RS for resistance in series. And just to show you how you would do that on paper, for example, you would say RS is equal to R1 plus R2 plus R3, or 50 ohms plus 30 ohms plus 75 ohms, and that gives us 155 ohms. Okay, so RS we know is 155 ohms, and don't forget we have the battery here, 9 volts. Okay, so that's the first step, is to break your circuit down into equivalent resistance all the way down, as far as you can go. This one's a one-step problem. You're going to go from here to here, so it's the simplest of all. Okay, and again, we want to figure out what we don't know. All right, well, what we don't know is we don't know the current. Okay, so I'm going to call this I. I'm going to call it IN. Some will call it I total. It's the current going into the circuit. Okay, it's the current coming out of the battery, and it's also the same as the current going into the battery. It's one path, so it has to be the same. All right, so do we know the voltage drop across this resistor? Yes, we do, because we can go from the resistor to the battery, to the left side of the battery, or the right side, and we can go from this side of the resistor to the other side of the battery without branching. Okay, there's no branch there, or rather, there's no component we have to go through. There's not another resistor here. If you look up here, the voltage drop, we don't know the voltage drop across the 50 ohm resistor, for example, because we can't go from the resistor straight to the battery. We can go from the left side of the resistor to the right side of the battery. That's no problem. But when we go from the right side of the resistor to the battery, we run into problems because we don't know what the voltage is at that point, because we have a resistor here and we have a resistor here. So we can't go all the way to the battery unimpeded. So that's why we break it down like so. So we know that the voltage drop, okay, across the resistor, across the series resistor, is equal to 9 volts. We know the resistor is 155 ohms. So the only thing we don't know is IN, the current going in. So let's use Ohm's law. So we know that delta V is equal to Ri. More specifically, the delta V across the series resistor is equal to the resistance of that series resistor times the current going in. Whatever you call it is fine. Just label it. All right. And now we want to know what IN is. And so that's delta Vs over Rs. And that's going to be 9 volts over 155 ohms, for a total of 0.0581 amps. All right, so this is the thing that we have discovered, right? And so we now know that IN is 0.0581 amps. Not that you need to do this, because the SI unit is in amps and not milliamps, but it's often easier to write as milliamps. And of course, this is 58.1 milliamps. If you want to write it like that, I find it easier to write a bigger number than a number with that's got a lot of decimal places there and there. Okay, so why do we do this? Why do we care about this? Well, we care about this because now we know the current coming into the circuit, and remember that's going to be the same current coming in this way. So this is our I in, okay, and so now we know that the current I going through the 75 ohm resistor is the same as I30, is the same as I50. Okay, all of these are the same because they don't branch. All right, so what we have to do, right, we're going to come down here, we're going to do our work down here. Sorry about that. So I guess what we can say, you know, to make sure that the teacher knows that what we're talking about is that we know what we're talking about. IN is equal to I50 plus I30 plus I75. I just use these numbers here to represent the different ohms up here. Okay, you can call it I1, I2, I3 if you want to, but this just helps me figure out which I is which, and we know that that is 0.581, 0.581 amps. Okay, so that we know, and so now let's calculate the voltage drop across each resistor. Okay, the voltage drop, in other words, what would the voltmeter, if we read the voltmeter there, what would it read? What would it read across this one? What would it read across this one? All right, and so, oh look, that's just Ohm's law. The voltage drop across a resistor is equal to the value of that resistor times the current flowing through it. And now we know everything. We know the current, rather, and we know the resistance, so voltages should be easy. So delta V50 is equal to R50 times IN, okay, or I50, whichever you want, because it's all the same. And this is just Ohm's law. So that's 50 ohms times 0.0581 amps, and that gives us 2.905 volts. We can do the same thing for the 30 ohm, the 30 ohm resistor. Oopsie. Handy eraser. And it's probably not important to write that. You've already written it here. We see that there's just going to be a pattern here. Always double check as you go. Double check as you go. You know, it's easier to check as you go than to go back and rework these problems. They're long. These problems are not easy. I always find it better to check as I go, you know, make sure that I double check my calculations. Do the numbers make sense? Okay, so we think we're done, right? And you know, who knows? Does this make sense? I don't know. So what we do is we check, okay? So what's the check? So we assume that the currents are all the same, right? Because they're in series, but maybe we made a mistake. Maybe that's not true. Let's see if it is true. Well, one thing we know about currents, about voltages rather, is the voltage drop, the total voltage drop across the entire circuit from this point to this point, okay, is 9 volts. And we know the voltage drop from this point to this point is also this voltage plus this voltage plus this voltage, right? Because you can go this way and read 9 volts, or you can go all the way through and it should be 9 volts. In other words, when you look at your resistors in series, we see that the voltage drop across the series resistor should equal voltage 1 plus voltage 2 plus voltage 3. the drop across each of the resistors. Okay, so let's do that check right now. Let's do a check. Okay. And if you have time to do it on a test, I would highly recommend it. You can kind of just quickly scan these. You don't have to do it super fast, but that plus that plus that looks like it's going to be close to 9 volts. So we're probably in the ballpark. Let's just do it for real. Okay, so delta V in or delta Vs is equal to delta V1, or sorry, I'm going to stick with my nomenclature, delta V50 plus delta V30 plus delta V75. Okay, and that is 2.905 volts plus, I'm going to run out of room, sorry about that, 1.743 volts plus 4.3575 volts, and that gives us 9.0055 volts, which should be 9 volts, and that is good enough for government work. So we are happy with that, and we know that this problem is correct. All right, I'll solve the next problem in the next video.